The original spanning tree protocol was developed way back in the mid-1980s by Per-vlan. This was a long time before switches, as we know them today, even existed. What you're seeing here is the original paper published in 1985 outlining how spanning tree works. And it worked well for its time. But back in the early 90s, the demand on networks wasn't what it is today. They didn't connect phones to their network. They didn't have mobile devices or high-speed internet. So if it took a whole minute for an interface to come back up, that wasn't considered a big deal. It wasn't long before this needed to change. So one of the improved versions of spanning tree, called Rapid Spanning Tree Protocol, was released with the aim of improving how quick a network change is detected and handled. So we're going to take a look at what has changed in Rapid Spanning Tree and how it achieves this fast convergence. Just because spanning tree has been improved on doesn't mean we need to throw away everything we've learned. There are a lot of similarities. For instance, there is still a root bridge. BPDUs are still sent through the network. Switches still need to find the best path to the root bridge. And links are still blocked to prevent loops. So then, what's changed? Well, for one, all switches actively send BPDUs, not just the root bridge. The BPDU format has changed a little to include more information. There are a few new port states to supplement the blocking state. There are improvements to bring ports up quicker. And Cisco have added their own Per-vlan technology. We're going to take a look at all of these changes in this video. So considering there's a few versions of spanning tree, how do you know which one your switch is running? Once again, we come back to the old show spanning tree command. On this switch, we see that we're running a version of spanning tree called IEEE. This is the original version of spanning tree. Usually, Cisco switches will run some type of RSTP by default. That means that you can take a brand new switch out of the box, connect it to your network, and it will automatically have RSTP protection. But we just can't leave it at that. We still need to know how to tune it to our needs, and how to troubleshoot something if it breaks. Let's start by seeing how we can change the version that we're using. We do this with the spanning tree mode command. And you'll see that there's a few options here. Rapid-pvst is Cisco's version of RSTP. I say Cisco's version, as they have added features that aren't strictly part of the RSTP standard. Don't worry, we'll cover those a bit more later. Now if we check the version once again, we can see that it has been changed to RSTP. Now, as usual, this video has plenty of quizzes that you can test yourself out on, and we're starting to get you to think a bit more outside the box. The basic concept of bridge IDs are still the same in RSTP. That is, the lowest bridge ID becomes the root bridge. But if you take a look at the bridge priority, you'll notice that something doesn't quite look right. In the last video, we said that the bridge priority was in increments of 4096. But here the value is 61,441, which clearly is not divisible by 4096. So what's happening here? In RSTP, the BPDU message now includes a system ID extension field. On a Cisco switch, this is basically the VLAN ID. And that's why we see the bridge priority broken down into two parts here. The priority and the Sys-id-ext. The system ID here is 1 because we're looking at VLAN 1. You should also notice that the bridge ID priority is different to the root ID priority. This tells us that the local switch is not the root bridge. Let's take a look at our other switch. Notice here that it says this bridge is root. This means that the switch we're currently logged onto is the root bridge. Quite simply, if you don't see this, some other switch is the root bridge. Let's take a look at BPDUs again for a minute. In the original spanning tree protocol, only the root bridge would generate BPDUs, and other switches would forward them through the network. The only exception to that is with TCNs, when a switch would use a BPDU to notify the network of a topology change. In RSTP, all switches now send BPDUs to their neighbours. These are a type of hello message to identify themselves and to learn about the other switches they're connected to. Individual BPDUs are no longer flooded or forwarded through the entire network. BPDUs are now sent only to the immediate neighbour. A significant advantage of this is being able to use BPDUs to see if an immediate neighbour is up or down. If 3 BPDUs go missing in a row, then the neighbour is considered to be down. BPDUs are sent out at regular intervals according to a hello timer. This is still every 2 seconds by default. We can change that timer if we want to. In configuration mode, we use the spanning tree command. Notice that we have to include a VLAN number. This is a Cisco thing. They require configuration to be applied per VLAN. And we include the hello time keyword and the time in seconds that we want. Now a quick architectural question for you. Why would we want to control where the root bridge is within our topology? When it comes to ports, some things change and some things remain the same. The root port, for example, is the same. There is still one root port per switch, and it still points out the best path to the root bridge. The only exception, of course, is the root bridge itself, which does not have any root ports. All ports on the root bridge are always designated ports. Speaking of designated ports, they're the same too. These are ports that point away from the root bridge and can still forward regular traffic. Each network segment can only have one designated port. If there were more than one, there would be a loop. What do I mean though when I say network segment? In nearly all cases these days, this is a link between 2 switches. The segment is the link itself, and there are only 2 devices on this segment. But a more complicated scenario is where you might have an old-fashioned hub or a dumb switch or something like that. In a case like this, more than one device can connect to the single segment. This is rare these days though. We shouldn't be seeing hubs anymore, but it is still possible, so be aware of it. If this does happen, if you do find a hub in your network, be aware that you can only have one designated port for the entire segment. If there was more than one, we would definitely have a loop. Therefore, one of these ports would need to be blocking instead. The blocking port is where things get interesting. Blocking ports can now be categorized as either alternate ports or backup ports. Any type of blocking port will block regular traffic, but still allow BPDUs. In fact, a port must be receiving BPDUs to be in a blocking state. Of course, you might wonder why this is the case. First, remember that all switches send BPDUs to their neighbours. If a port is not receiving BPDUs, then it is not connected to another switch. It's probably connected to something like a PC, a printer, a server, or some other end device. We can't create loops on interfaces connected to these devices, so these ports do not need to be blocking. As I just mentioned, blocking ports can be alternate or backup. An alternate port is one that has received a superior BPDU from a different switch in the same network segment. The network segment in this case is just that link between the 2 switches. This here is an alternate port, as it is an alternate path to the root bridge. It's ready to take over if the current root port fails. Backup ports come into play when there is a shared segment. That is, something like a hub that allows 2 or more switches to connect to each other. In our example, one switch has 2 links. One link on this switch becomes designated. On the other switch, the port is blocking. This would be an alternate port as we just discussed. Now back on the switch with 2 links, something interesting will happen. The switch will see its own BPDUs. That is, each port will send BPDUs, and the other port will receive them. Only one of these can be designated though, so the other must be blocking. But because the switch receives a BPDU from itself, the blocking port will be a backup port. It's called a backup port as it's the backup to this segment. Just remember, as we previously said, that hubs are rare, so you're unlikely to see backup ports. If you do see backup ports in your network, you probably have a hub somewhere, and you should probably take steps to replace them. We can examine the output of show spanning tree to see these port types. Here we can see the role, which would be root, designated, alternate, or backup. The status, which can be forwarding or blocking. And of course the cost, which we spoke about last video. The cost is determined by the speed of the port. There may be times when we want to override this though. Perhaps we want to make traffic flow over a different path for troubleshooting purposes. To do this, we configure an interface, and then we enter the spanning tree cost command. The cost is any numerical value. Of course, we should verify our change with show spanning tree. And you'll see here that the cost has changed. This has in effect changed which ports are root and which are alternate. So have a look at this topology. Can you figure out what would happen, from a spanning tree point of view, if the red link were to break? In the original spanning tree, a port needs to work through the blocking, listening, learning, and forwarding states. All up, it would take about 50 seconds for a port to come online, which is far too long in a modern network. RSTP addresses this issue by changing the states to discarding, learning, and forwarding. The old blocking and listening states have effectively been combined into discarding. But the big change is how all these work. They don't have timers anymore. Instead, they have a negotiation procedure. As before, when an interface first comes up, it is in the blocking state, so a loop can't form before it's detected. For our example, imagine that we're adding a new switch into the network. There's no loop here, but spanning tree doesn't know that yet. The switches will start sending BPDUs, which starts a negotiation process called a sync. This gets a bit complicated, but basically they use new fields in the BPDU message to share information. They negotiate the link to the root bridge first, and enable that link. At this point, the downstream links are still blocked. One switch will propose which links should be forwarding and which should be blocked. The sync process then completes for downstream switches, and the appropriate links transition to forwarding. Now, I have very much oversimplified this process. The point to remember is that RSTP takes a much more active approach in bringing up the interfaces. There are no timers, which means interfaces come up faster. This approach means RSTP can respond very quickly to changes in the network. But don't take my word for it, let's see it in action. First, we're changing our flavor of spanning tree to PVST. This is one of Cisco's versions of the original spanning tree standard. I'll get to why this is called PVST later. Next, I'm enabling spanning tree general and event debugging. So in case you've forgotten or you haven't come across debugs yet, debugging is getting extra logging information from our switch so we can use it for troubleshooting. I have a separate video on that if you want a review on how that works. If we're on the console port, which I am, we will see all debug logs in real time. However, if you're connecting to a switch with SSH or Telnet, you need to run the terminal monitor command first. What this does is sends the logs directly to your terminal session so you can see them. You'll notice that we're already getting a few logs, as there's always something happening. I'm now going to bring up a new link on gigabit 02. Notice that we can see the interface going through the various states. First listening, then learning, and finally forwarding. As you can see, it takes too long for a port to transition to forwarding. I'm now going to shut that port down so we can try it in RSTP. Of course, we'll get a few more debug logs along the way. Now we'll change to RSTP mode. This in itself will generate a lot of logs. We'll just wait until they're finished. Okay, that looks stable now. And now I'm going to bring up gig 0/2 again. And that's done. See how much faster that was with RSTP? We can go back and look at a few of the steps that it took, such as selecting designated as the port role and sending the RSTP proposal. Of course, you should always remember to disable any debugs when you're done troubleshooting. Got another quiz question for you, but I don't think you'll find this one very hard. When we think of spanning tree topologies, we can think about different ways that ports can behave. So far, we've mainly talked about the links between switches. As far as RSTP is concerned, these are either point-to-point ports, which is a direct connection between two switches, or shared ports, which connect to a shared segment, like having a hub in your network. We've looked at both of these already. But there's a third type we haven't looked at, called an edge port. This is where edge devices connect. These are devices like PCs, printers, routers, basically anything that's not connecting switches together. Why is this important? Because spanning tree is there to stop loops. And where do loops occur? In devices that forward layer 2 frames, so basically hubs and switches. Edge devices do not forward frames, so they do not cause loops. So as you can see, there's no reason to worry about BPDUs, port states, blocking ports, that sort of thing, when we have an edge device connected. Now in the old days, that would be a problem. Because even if we're connected to an edge device, it would still take 50 seconds for that port to come online, and that's just wasted time. To address this, but even before RSTP was invented, Cisco created a feature called Port-fast. It was such a good feature that when RSTP was released, it became a built-in part of the standard, which we now know as the edge port. When we know that certain ports are for edge devices only, we can configure them with Port-fast. So let's see how that's done. Under Interface Configuration, we enter the spanning tree Port-fast command. Despite being part of the vendor-neutral RSTP, we still call it Port-fast when using Cisco switches. Just remember that other vendors will call it an edge port. Notice that we're given a warning. We have authorized the switch to bypass many of the spanning tree procedures on this port in order to get it to perform better. This is fine, but be aware that connecting a switch here while Port-fast is active may introduce a loop into the network. If we look at the spanning tree details again, we can see that this interface is now listed as an edge port. It also goes straight into the forwarding mode, bypassing the discarding, learning, and forwarding states. It's also worth noting that if this port goes up or down, it will not trigger a TCN to other switches. Practically though, what happens if someone plugs a switch into an edge port? Whether it's malicious or accidental, this can happen. By default, this might introduce a loop into the network, which is of course very bad. Does this mean that Port-fast is just too risky to use? Not necessarily. There's another feature that came along with Port-fast called BPDU guard. Now, as far as I know, this is not on the exam, but I feel it's too important not to mention it, at least briefly. So imagine we have configured an edge port with Port-fast, and we connect a workstation. To be safe, we also configure BPDU guard. Then someone comes along, disconnects the workstation, and connects a switch. When the new switch is connected, it will start sending BPDUs. The original switch will see this, and it will think, hang on, that's not right. There must be a switch connected. The port will then lose its edge port status and it will become a regular port. In this way, our network is still protected from loops. I have a couple of trickier questions for you this time. You might need to do some of your own research on these ones, but don't worry, it'll be time well spent. The original spanning tree, known as 802.1d, has quite a few drawbacks in the modern network. We've looked at a few of them in this video. Over time, there have been a few improvements to the original protocol, and a few new variants of spanning tree, not all of which are shown here. Cisco even had a few proprietary versions which only worked with other Cisco switches. There have also been vendor-neutral versions that work on all switches, like RSTP. To be honest, these take a lot of Cisco's improvements like better timers, port roles, and other features, and they make them standards. So RSTP is the vendor-neutral improvement on spanning tree. Cisco's implementation of this is called Per-vlan rapid spanning tree. This means that Cisco's enhanced version of RSTP is aware of VLANs, while the official version of RSTP is not. Another version of spanning tree called Mstp is the vendor-neutral option that is VLAN aware. Okay, So what do I mean when I say VLAN aware or per-VLAN? Well, traditionally, the spanning tree topology is the same for the entire switching domain. If a port is the root port, it's the root port for all VLANs. If a port is blocked, it is blocked for all VLANs. In the per-VLAN model, there is a separate spanning tree instance for each VLAN. Take this topology for example. We have two VLANs, 10 and 20. We can configure different priorities, route bridges, and link costs for each VLAN. This means that the switch selected to be the route bridge for VLAN 10 may be entirely different to the switch selected to be route bridge for VLAN 20. There are pros and cons to this approach, of course. In a traditional model, some links would still be blocked. These links would be then sitting there idle all the time, essentially being wasted. In our per-VLAN model, a link may be blocked for VLAN 10, and a different link is blocked for VLAN 20. This means that we're utilizing all our links. On the other hand, the switch needs to maintain a separate instance for every VLAN, even if they have the same configuration. If you have a lot of VLANs, then your switch will have a lot of spanning tree processors. This puts more load on the switch's hardware. MST, that's multiple spanning tree, is a reasonable alternative in this case, but that's outside the scope of a CCNA level video. Let's see how this looks on a switch. First, we're creating our two VLANs, 10 and 20. We want this switch to be the route bridge for VLAN 10, but not for VLAN 20. This is done by changing the bridge priority as we saw in the last video. This time I'm going to show you a shortcut. We're going to run spanning tree, VLAN 10, route primary. This is a macro or shortcut on Cisco switches that sets the bridge ID for us, so this switch will become the route. By specifying VLAN 10, this change will only happen for the VLAN 10 spanning tree instance. We can do the same for VLAN 20 using the secondary keyword. This will set a bridge priority that's a little worse than the current route bridge, but still better than other switches. So if the route bridge fails, this switch will be the next in line to take over. We can now take a look at the result with show spanning tree VLAN 10. This is the same as show spanning tree command we've been using. It's just limiting the output to VLAN 10 information only. We can indeed see that this is the route bridge for VLAN 10. Let's do the same for VLAN 20. You can see here that some other switch is the route bridge for VLAN 20. The local bridge priority is a little worse than the route bridge. Question 10 here is the big one I want you to think about. I have faced this question in the real world and it's likely that you will too. You will need to put in some additional research to find the answer. We have a two-part lab today. In the first part, you need to implement RSTP and add general enhancements. In part 2, someone has broken our network. You need to find the fault and repair it. We're now going to move on from spanning tree. Head over to the next video, which looks at bundling multiple links into a single ether channel.